So now, Kay-Markus Wulf from CSI in Germany is talking to you, presenting a process chain for having ultra-lightweight seats, for example, components for the car interior. And we are very much interested in listening to you, Kai.
Okay, then hello everybody. I would like to welcome you all at the Elmia subcontractor today. My name is Kay-Markus Wulf, and I'm the project leader of the NaMiKo, the part of CSI Entwicklungstechnik, the part I would like to show you today. In the next few minutes, I can explain the current status of the digital process chain to you. My focus here is also clearly on sustainability, because the digital process chain is a wonderful how you can combine different aspects of sustainability, such as ultra-lightweight construction paired with sustainable materials. I would like to do this by showing you the path that the digital process chain has taken from the ultra-lightweight seat through the armrest to the NaMiKo. But let's start with why we're doing this and clarify a few general issues. The Earth Overshoot Day, an annual campaign by the Global Footprint Network organization, is the day of the current year when human demand for renewable resources exceeds supply and the Earth's capacity to reproduce those resources for that year. As you can see, the Earth Overshoot Day has come earlier and earlier in the recent years. If it was still December the 7th in 1970, in 2021, we will have reached the day on July the 7th. Of course, there are also a few positive impacts in history, such as in 2022. We all still remember the pictures from Venice, where the boats sailed on clear water in the canals, which were always very turbid up to now. Dolphins have also not been seen in the bay for a long time. But this was all due to the pandemic, and in 2021 we are back to the level before Corona. For Germany, the Earth Overshoot Day was on May the 4th this year. From that day on, we lived in Germany beyond our means. So the Earth was not able to reproduce our resources, what we used from May the 4th this year. Global warming is also an important factor. With such tools as the digital process chain, we can decide which side of the future we want to be on. And I don't think it's difficult to choose when you look at these two ways. I would like to live on the right side. Sustainability means business success. I don't think I need to go into more detail about the magic triangle of the sustainability during my presentation. We all can imagine what happens there. On the right side, we have the material energy consumption and CO2 emissions, like mass or material processing and CO2 footprint. On the left side, we have the natural resource use, so material availability, water management, waste management. And at the bottom part, technology parameters, so the industrialization of the whole thing. These three factors are, for our magic sustainability triangle, important. But let's start with some basics. On the basics, one of the basics here is the XFK and 3D technology, which was and is being promoted by the company AMC. There are already many advantages here which are very important for sustainability, such as the almost waste-free production or the ultra-lightweight principle. We have here in XFK and 3D, no waste of material, as already said. We have an attractive string art design. We have a versatile process, so we can really go on every new product, or we can do it nearly wherever we want to have it built for substructure parts, or we can use it for visible parts, as you will see in the NaMiKo. But however, one of the essential points in XFK 3D is the digital process chain, and that is one of the core competences of CSI Entwicklungstechnik. The digital process chain is one of our core competences, and front-loading is an important term here. We start by recording the load spectrum and the load path, which are then displayed in a previously created installation space model, from which we obtain the topology optimization. Based on this topology optimization, we can now develop our design of the component and create the first winding plans on it. This design model is now checked and optimized in the calculation and simulation until these results match the desired values. Of course, tool development is also an important point. This also takes place digitally in order to save as many resources as possible. At the very end, we only build our prototype, which, however, already corresponds to 95% with the optimal series component. As you can see, the digital process chain is indispensable when it comes to saving resources, and thanks to the refinement of the individual process steps, is now realistic and reproducible. Here's an example how the digital process chain can be further developed. This is a CSE tool developed by a colleague of mine, and this tool can create an optimized winding plan fully automatically using only the three-dimensional coordinates in the space. And it's searching for itself the shortest and easiest way to wind our part. Here is the part is a space frame for a car at the moment. But enough of the general part. Let's come to the ultra-lightweight seat, also known as ULBS. Now that you're all probably familiar with the ULBS, I hope so, here are just a few quick facts about it. The ULBS was created by CSE in 2019 and was built by a colleague of mine. The ULBS was being wrapped in an ultra-lightweight construction. It is a proof of concept, but really only a proof of concept. It was not built for any car or anything else. It was a standalone demonstrator to see how XFK in 3D could work. Due to the very short development time, the ULBS was still hand-wound and a well-known material, carbon, was used. The result is still impressive when you look at the total weight of around 10 kilogram. So it was not really heavy, and for the development time at 2019, it was, I think, nearly about 20% lighter than every seat that was on the market. But how does this ULBS fit into our magic sustainability triangle? As we can see, this consists of the three topics of material or energy consumption and CO2 emissions, use of natural resources, and the technology parameters or industrialization. With the ULBS, we have at least earned a green tick for the economical use of the material thanks to the ultra-lightweight construction, saving material here. With the armrest, we have already gone one step further. But let's start at the beginning of the 2-month development period. As we have already heard, in theory, we have also started recording the load spectrum for the armrest. The first consideration was which load case we need to define. For this, we came to the result of 2 load cases. Load case 1 on the left describes the static condition when the rider of the racing bike is lying with his arms in the receiving shells. And load case 2 on the right-hand side then again shows the process of placing the bike in the receiving shells, when the driver holds onto his handlebars before his arm slides into the shells. For this, we have assumed realistic measurements and weight, as the average weight of an ordinary triathlete is around, I would say, perhaps 70 kilogram. In the next steps, we created an installation space model based on the concept sketches that we received from our semi-professional triathletes. With the help of this load and the installation space model, the simulation gave us the topology model for the base plate and the armrest shells, which you can see on the right-hand side. You can see that from our assembly space model, here we have only given a few lines, a few paths, which are really interesting for us for taking on the load and the forces. The design of our armrest is very familiar to the topology model you saw on the previous page. With the design model, we also created the first winding plan and gave it to our supplier for approval. After a few small optimizations, we were then able to submit our design model for calculation and simulation. And here in these two pictures, you can see at the animations, the shifts in our calculation model are not large. We have a maximum displacement of about 1.5 millimeter for the first load case and 11 millimeter for the second load case, what is not really a lot displacement. After the calculation in a simplified beam model also met our requirements, we were able to start the production. The tooling was done or was took over by our supplier for this and ended up giving us the great final product. Compared to solutions currently available on the market, we have saved an incredible 60% in weight with the help of XFK and 3D technology. The armrest weighs 66 grams, while the structure, including the sockets, weighs only 51 grams. That's not really, that's not really much. When you take a look at the market at the moment, possible solutions for carbon weigh about, I would say, 200 grams, our triathletes told us. With a safe factor of 2, we have achieved a maximum load capacity of 140 kilogram there. We also used sustainable materials for the armrest. Here, basalt was used as the fiber for wrapping, and 100% organic cork mat was used. Only the bushings, what you can see at the bottom view, are done by 3D printing. There we can use also sustainable materials for that, so that we have a 100% sustainable product at the end. At the end of the armrest, let's look again at our sustainable triangle. Compared to the ULBS, we have not only fulfilled the point of material use, but also the point of natural material use. Thus, 2 out of 3 corners of sustainable are already fulfilled. So only 1 is left. So, however, the aim of the NaMiKo project is to fulfill the last aspect, to fulfill the industrial part aspect. As you will see at the beginning, the first steps of the center console are the same as those of the armrest. Let's explain at the beginning, a few points of the NaMiKo. The name NaMiKo comes from nachhaltige Mittelkonsole. It's German. It means sustainable center console. The beginning starts here as well with an construction space model that was created, and the whole thing was created with the help of the Altair company. In addition, Altair has also taken over the creation of the topology model with the help of BMW Group, the BMW M Group. It's our associated partner at the NaMiKo project, and we had a real car to build this center console for. Based on this topology model and the current installation space in the BMW M4, our design department at CSE has started to create initial design ideas. As you can see in the picture, the topology model, which can be seen in blue in the background, served as the basis for this design. There were, of course, more ideas for the design. I brought the two most impressive with me today. After the project team, consisting of our project partners AMC, DITF, CSE and the BMW M Group, decided on a design. This was then worked out in more detail, and this rendering was created. Together we discussed a few more ideas and came up with the following design for our design demonstrator, which should be seen at the fair today, but our first demonstrator is at the moment assembled to the BMW M4 prototype. And the second demonstrator was not really finished for the fair. I'm very sorry for that. Here, too, one of the most important core competences of CSE comes into the play, namely the 3D implementation in the well-known design program CATIA. Our development department was faced with the challenge of integrating the central console element from BMW with the gear selector and the electronics into the design, as no quickly implementable idea could be implemented in the last 6 months. This is just the current status of our design demonstrator, as it should normally be at your fair today. You have already seen, perhaps the future vision of our NaMiKo, and we are going to have, I think, 2 more years at this project, and it's a funded project from the German government, so there's enough time to develop it to perhaps a more detailed and good-looking status. The next step was the calculation of the XFK support structure. A weight of approximately 80 kilogram in the -z direction and 20 kilogram in the y direction was assumed here if a passenger supports himself a little on the center console when getting out, for example, because the BMW M4 is a really low car, so it's quite a little bit different for people to get out of this car. The whole thing was calculated according to the rigid body method, which is completely sufficient for the first shot of the simulation. Here too, the calculation results were outstanding for the first shot of the design and the layout of the supporting structure. We currently have a maximum displacement of approximately 3.7 millimeters in the y direction and 0.4 millimeter in the z direction. For the Z direction, we have assumed the load case that perhaps now, I think on Sunday, the World Championship in football will start, and some guy will stand on the center console and is looking on out of the roof window of his BMW M4. For that, we have the 80 kilograms in the -Z direction. After all these process steps, we decided to build a design demonstrator so that you can see the whole thing in hardware and not just really virtual imagination is necessary. This demonstrator will not be subjected to any tests, as this would contradict the digital process chain. It is purely for the purpose of better communicating the design in order to be able to understand it in hardware and to get a little bit more feeling of this whole product. But why exactly is the NaMiKo now a step forward in the development of the digital process chain compared to the ULBS? On the one hand, we have a sustainable material here. Instead of carbon fiber, as in the ULBS, we use rayon fiber and bio-based resin here. In addition, the center console is intended for a real vehicle, whereas the seat was only a standalone proof of concept here. Also, all components will be integrated into the digital process chain within the next 2 years of the project, not just the XFK and 3D structure. Industrialization is also an important point. If the ULBS is still hand-winded, the NaMiKo will be fully automated robot-winded. The tool design and layout will also move more into the focus at the digital process chain, not at least because of the consolidated XFK 3D structure. That's another difference between the ULBS and the NaMiKo, that we have it here consolidated, the XFK and 3D structure. Because of this consolidated structure, we can use it in the automotive interior. So let's take a look at our triangle again and tick off the points that are achieved with the NaMiKo. With the XFK and 3D structure and the other lightweight construction technologies used, we have reached the point of using materials. The use of rayon fiber, bio-based resins, and the material from BComp company means that the aspect of sustainable and natural resources is also taken care of. With the development of fully automated winding and the consolidation of the supporting structure, an important part of the technology parameters and industrialization can also be regarded as completed. As you can see, the NaMiKo fulfills all aspects of the sustainability triangle. But let's take a look. Since we still have 2 years of development ahead of us and are far from having reached the end of our possibilities, we should also take a look at what is on our to-do list for the NaMiKo in the near future. As previously mentioned, it will still be a challenge to let the NaMiKo wrap fully automatically in combination with a consolidation of the supporting structure. The digital process chain is supplemented by the remaining components, such as the center armrest, the covers, and the smart textiles. The already refined calculation must now also be used. We will analyze the fibers on a single strand level, and also the knot analysis at the turning points needs to be considered more deeply. Consolidation is also an important part of this calculation, of course. After the overall project is named NaMiKo Smart, the smart textiles must be integrated into the overall center console system in the future. Yeah, and I'm already looking forward to presenting the final result of the NaMiKo project to all of you in 2 years, I hope so. And as I'm convinced that with this project, we will be taking a big and important step in the area of sustainable and future automotive development. I would like to thank you for the invitation to the Elmia Subcontractor Fair, for the opportunity to bring the digital process chain a little bit closer to you. Thank you at the same time for your attention, and I hope you enjoyed today's day at the Elmia Subcontractor. Thank you very much.